BalamSemiconductor Podcast, Episode 3, Combinational versus Sequential Circuits in Verilog. Welcome to BalamSemiconductor, the podcast where circuit design comes to life. I'm Carlos Alberto, and in this episode, we're going to uncover one of the most fundamental distinctions in digital hardware design: the difference between combinational and sequential logic. What is combinational logic? Combinational logic refers to circuits whose outputs depend only on the current values of their inputs. There is no memory or feedback mechanism. The output reflects the logic computation in real time. Classic examples include adders, multiplexers, decoders. In Verilog, combinational logic is typically described using assign statements, always _com, system Verilog, always at asterisk, Verilog. For instance, a 4-bit adder can be written simply as assign sum equals A plus B. This line ensures that the sum will immediately reflect changes in A or B. You can also use an always at asterisk block to describe combinational logic, especially when using conditional structures such as if-else or case. It's important to cover all possible input cases in a case or if-else structure. Failing to do so can unintentionally infer latches, which introduce memory-like behavior and break the nature of pure combinational logic. In FPGAs, combinational logic is implemented using lookup tables, LUTs, inside configurable logic blocks, CLBs. In ASIC design, the same logic is mapped to standard cells in the logic library. ASIC implementation of combinational logic. In application-specific integrated circuits, ASICs, combinational logic is implemented using standard cells from a technology library. These standard cells are pre-characterized building blocks such as logic gates, multiplexers, and arithmetic units designed for a specific CMOS process. When your RTL is synthesized, the synthesis tool maps your Verilog description into a netlist of standard cells, optimizing for timing, area, and power. For instance, a simple assign out equals A and B will be mapped to a 2-input and gate from the library. More complex logic may be mapped to compound gates or optimized Boolean expressions. One advantage of ASICs is that these gates have known delay characteristics, allowing for fine-grained timing analysis and optimization. This contrasts with FPGAs, where LUTs are more generic but less efficient in terms of power and speed. Furthermore, ASIC flows allow for logic gate sizing, adjusting transistor widths in standard cells to balance drive strength and power, something that is not possible in fixed FPGA logic. What is sequential logic? Unlike combinational logic, sequential logic includes the concept of state. Outputs depend not only on current inputs, but also on past inputs stored as internal state. Typical components include flip-flops (TJK), counters, finite state machines (FSMs). In Verilog, sequential logic is described using edge-sensitive blocks. Always at posedge CLK or posedge reset begin. If reset Q equals 0, else Q equals D. And here, the value of D is stored into Q only on the rising edge of the clock. The reset condition ensures initialization, which is essential in real-world systems. This introduces the notion of time and synchronization, which is what enables building memory elements, control units, and pipeline data paths. Key differences and design implications. Timing. Combinational logic responds immediately. Sequential logic depends on the clock. State. Combinational logic is stateless. Sequential logic stores state. A design discipline. Combinational logic requires careful case coverage to avoid latches. Sequential logic requires clean clocking and reset strategies. Understanding when to use each type is crucial. For example, an ALU's arithmetic unit is combinational. A register file or counter is sequential. Most digital designs are a hybrid of both data flows through combinational logic and are stored via sequential elements on each clock cycle. That wraps up episode 3 of BalamSemiconductor. Today, we clarified the difference between combinational and sequential logic, explored how to code each one in Verilog, and touched on their implementations in FPGAs and ASICs.